Riemannian geometry is a branch of differential geometry that studies Riemannian manifolds. These are smooth manifolds equipped with a Riemannian metric, which is essentially an inner product on the tangent space at each point that varies smoothly from point to point 1. This metric gives rise to local notions of angle, length of curves, surface area, and volume. By integrating these local quantities, one can derive global properties. The field was founded by Bernhard Riemann in the 19th century, and it generalizes the differential geometry of surfaces in three-dimensional space to higher dimensions. 1. Riemannian geometry allows for the examination of a wide range of geometries with metric properties that vary from point to point, including the standard types of non-Euclidean geometry. Every smooth manifold can admit a Riemannian metric, which can be used to solve problems in differential topology. In Riemannian geometry, concepts such as geodesics, the generalization of the idea of a straight line to curved spaces, are studied. Geodesics are the shortest path between points on a curved surface or manifold and play a crucial role in the theory. The development of Riemannian geometry has had a significant impact on various fields of mathematics and physics, including the formulation of Einstein's general theory of relativity. It has also influenced group theory, representation theory, analysis, and spurred the development of algebraic and differential topology. 1. Here's a basic mathematical representation of a Riemannian metric. If M is a Riemannian manifold and T_Pm is the tangent space at a point P, then the Riemannian metric G at P is a positive definite inner product on T_Pm. This can be expressed as Gp v w equals v wp, where v and w are vectors in the tangent space T_Pm, and \langle_dot\rangle_p denotes the inner product at point P. For a more in-depth understanding, you might want to explore further resources or academic texts on the subject. Certainly, geodesics are one of the central concepts in Riemannian geometry. They can be thought of as the generalization of straight lines to curved spaces. In the context of Riemannian manifolds, geodesics are the curves that locally minimize distance, making them the shortest path between 2 points in the manifold's curved space. 1. Here's a more detailed look at geodesics. Definition. A geodesic is a curve, \gamma t, on a Riemannian manifold, M, G, such that the acceleration of \gamma t is 0 when it is parallel transported along itself. This means that the curve has no intrinsic acceleration. Any change in the direction of the curve is due solely to the curvature of the space. 1. Mathematical expression. The condition for a curve, \gamma t, to be a geodesic can be expressed using the Levi-Civita connection, \nabla, of the manifold. A curve is a geodesic if T_gamma t equals 0, where \gamma t is the derivative of \gamma t with respect to its parameter t, which represents the velocity vector along the curve. This equation states that the covariant derivative of the velocity vector along the curve itself is 0. 2. Geodesic equation. In local coordinates, this condition translates into a system of second-order differential equations known as the geodesic equations. For a geodesic, \gamma t, with local coordinates, \gamma t, the geodesic equations are gamma I t plus tj t gamma k t equals 0, where \gamma I_jk are the Christoffel symbols of the second kind, which encode the manifold's connection coefficients and, consequently, its curvature. 2. Properties of geodesics. Local distance minimizers. Geodesics are locally the shortest path between points, but they may not be the global minimum due to the manifold's curvature. Speed preservation. If a geodesic is parameterized by arc length, i.e., the parameter t corresponds to the actual distance along the curve, then it moves at a constant speed. 1. Exponential map. The exponential map at a point P in the manifold sends a tangent vector v in the tangent space T_Pm to the point on the manifold reached by traveling along the geodesic starting at P with initial velocity v for unit time. 2. Geodesics are not only important in the study of geometry and topology but also in physics, where they describe the motion of particles in a gravitational field according to general relativity. In this theory, the geodesics of spacetime are the paths that free-falling objects follow. Geodesics play a pivotal role in the theory of general relativity, which is Albert Einstein's theory of gravitation. In this theory, geodesics are not just the shortest paths between points, but they also represent the paths that objects follow when they are moving under the influence of gravity alone, without any other forces acting on them. 12. In the framework of general relativity, gravity is not viewed as a force in the traditional sense but rather as a consequence of the curvature of spacetime. This curvature is caused by the presence of mass and energy, as described by the Einstein field equations. Objects move along geodesics in this curved spacetime, which can be thought of as the straightest possible paths given the curvature 1. Mathematical expression in general relativity. The geodesic equation in general relativity is expressed as ds2 d2x plus ds dx ds dx equals 0. Here, x⁻⁻mu represents the coordinates of spacetime, s is the proper time, or another affine parameter, and \gamma_mu_\nu_sigma are the Christoffel symbols, which encode information about the spacetime curvature 1. Physical interpretation. In a physical context, this means that a planet orbiting a star, for example, is not being pulled by a force of gravity in the traditional sense. Instead, the planet is following a geodesic path through the curved spacetime that is created by the star's mass. Similarly, the trajectory of a light beam passing near a massive object is a geodesic in the curved spacetime, which results in the phenomenon of gravitational lensing. 1. Geodesics and free fall. An object in free fall, such as a satellite orbiting Earth or a rock dropped from a height, is moving along a geodesic. This is why astronauts in orbit experience weightlessness. They are in continuous free fall around Earth, following the curved spacetime geodesics created by Earth's mass 2. In summary, geodesics in general relativity describe how objects move under the influence of gravity, providing a profound connection between the geometry of spacetime and the motion of objects within it. This concept is fundamental to understanding how gravity works on cosmic scales, from the orbits of planets to the bending of light from distant stars. Certainly, in the context of general relativity (GR), black holes are fascinating objects whose behavior is intricately tied to geodesics. Let's delve into how geodesics play a crucial role in describing black holes, geodesics in curved spacetime. In GR, spacetime is curved by massive objects like black holes. Geodesics are the natural paths that particles follow in this curved spacetime. Geodesics represent the motion of particles, such as photons or massive particles, when no other forces, like electromagnetic forces, are acting on them. For black holes, geodesics describe how objects move under the influence of gravity alone. Geodesic paths around black holes. When a particle, for example, a spaceship or a photon, approaches a black hole, it follows a geodesic path. Near a black hole, the curvature of spacetime becomes extreme due to the immense mass concentrated in a small region, the singularity. The event horizon, the boundary beyond which nothing can escape, marks a critical point. Geodesics near the event horizon are profoundly affected by the black hole's gravity. Properties of geodesics near black holes. Circular orbits. Stable circular orbits around a non-rotating Schwarzschild black hole correspond to geodesics. Photon orbits. Photons follow geodesics, resulting in the famous photon sphere around a black hole. These photons can orbit the black hole multiple times before escaping or falling in. In falling matter, matter falling into a black hole follows geodesics, spiraling inward due to gravitational attraction. Testing general relativity. Observations of stars orbiting supermassive black holes, for example, SGR** at the center of our galaxy, confirm geodesic behavior. Gravitational waves from merging black holes also follow geodesics, allowing us to test GR predictions. Event horizon and geodesics. Once a particle crosses the event horizon, its geodesic path leads inexorably toward the singularity. No force can prevent this motion, it's the ultimate downhill path in curved space-time. In summary, geodesics provide a powerful framework for understanding how particles move around black holes. They reveal the intricate interplay between gravity, curvature, and the fascinating properties of these cosmic enigmas. Inside a black hole, the concept of geodesics takes on an intriguing and complex character due to the extreme curvature of spacetime. Here's what happens to geodesics once they cross the event horizon of a black hole. Beyond the event horizon. Inside the event horizon, the roles of space and time coordinates interchange. What was once a spatial direction towards the black hole becomes a temporal direction inside it. This means that moving towards the singularity is as inevitable as moving forward in time. Inevitability of the singularity. All geodesics inside the event horizon, regardless of the initial conditions, will end at the singularity. The singularity represents a point of infinite curvature where the laws of physics as we know them break down. No escape possible. Once inside the event horizon, no geodesic can lead back out. This includes even those paths that are followed by light, which is why black holes appear black. Spacetime curvature. The curvature of spacetime inside the event horizon is so severe that all geodesics are directed towards the singularity. The Schwarzschild solution to Einstein's field equations describes this curvature for a non-rotating, spherically symmetric black hole. Tidal forces. As one approaches the singularity, the tidal forces increase dramatically. These forces can stretch and compress objects in different directions, a process sometimes referred to as spaghettification. Kruskal-Skores coordinates. To better understand the structure of spacetime inside a black hole, physicists use Kruskal-Skores coordinates. These coordinates reveal that the interior of a black hole is dynamically evolving and that the singularity is not a point in space but a moment in time. Quantum effects. Quantum gravity effects are expected to become significant near the singularity, potentially resolving the infinite curvature and providing a more complete description of the inner black hole dynamics. It's important to note that our understanding of the interior of black holes is still theoretical. The extreme conditions present significant challenges to both observation and theory. However, the study of geodesics in this context continues to be a rich area of research in theoretical physics. Wormholes are theoretical passages through spacetime that could create shortcuts for long journeys across the universe. In the context of general relativity, wormholes are solutions to the Einstein field equations, which describe the fundamental interaction of gravitation as a result of spacetime being curved by matter and energy. Here's how wormholes are connected to geodesics. Wormhole structure. A wormhole typically has two ends, each in separate points in spacetime, connected by a tunnel-like structure known as the throat. The throat of a wormhole is a region where the spacetime curvature allows paths that can connect two distant regions more quickly than would be possible through normal space. Geodesics and wormholes. In the vicinity of a wormhole, geodesics can behave unusually. Instead of simply being the shortest path between 2 points in spacetime, they can represent paths that pass through the wormhole's throat. There are two types of geodesics related to wormholes: regular geodesics, which have turning points larger than the throat radius and remain confined to one half of the wormhole, and singular geodesics, which funnel through the throat and connect both halves of the wormhole. 1. Traversable wormholes. For a wormhole to be traversable, meaning that something could physically travel through it, certain conditions must be met. These conditions often involve the presence of exotic matter with negative energy density to stabilize the throat and prevent it from collapsing. Implications for travel. If traversable wormholes exist, they could allow for rapid interstellar travel, effectively reducing the distance between 2 points in spacetime. This has been a popular concept in science fiction. Challenges and theoretical considerations. The existence of traversable wormholes is still hypothetical. Theoretical challenges include the need for exotic matter and the stability of the wormhole structure. Wormholes also raise questions about causality and the possibility of time travel, leading to discussions about the chronology protection conjecture. In summary, while wormholes are a fascinating theoretical possibility, their actual existence and properties, including their relationship with geodesics, remain speculative and a subject of ongoing research in theoretical physics. Riemannian geometry, named after the German mathematician Bernhard Riemann, is a profound and expansive field of mathematics that has significantly influenced the development of theoretical physics and various branches of mathematics. Here's a detailed account of how Riemannian geometry was created. The inception of Riemannian geometry. Bernhard Riemann's vision. Riemannian geometry originated from the innovative vision of Bernhard Riemann, who first presented the ideas in his inaugural lecture Über die Hypothesen, Wellster Geometrie zu Grunde legen, on the hypotheses on which geometry is based, in 18541. Generalization of surface geometry. Riemann extended the differential geometry of surfaces in three-dimensional space to higher dimensions. He introduced a broad range of geometries with metric properties that vary from point to point, including non-Euclidean geometries. 1. Key contributions and developments. Riemann's habilitation lecture. In his habilitation lecture at the University of Göttingen, Riemann laid out the foundations of what would become Riemannian geometry. He proposed considering a manifold, a generalization of surfaces, equipped with a metric that defines the distances within the space 2. Metric tensor and curvature. Riemann introduced the concept of the metric tensor, which provides a way to measure distances and angles in a manifold. He also defined a curvature tensor, now known as the Riemann curvature tensor, which describes how a manifold bends or curves. 2. Mathematical framework. Manifolds and metrics. Riemann's idea was to define a manifold with a smoothly varying metric tensor at each point. This tensor would allow for the calculation of lengths of curves, angles, and other geometric properties locally and globally. 1. Geodesics. Riemann's framework also naturally led to the study of geodesics, which are the shortest paths between points on a manifold, generalizing the concept of straight lines to curved spaces. 1. Impact on mathematics and physics. Synthesis of diverse results. The development of Riemannian geometry resulted in the synthesis of diverse results concerning the behavior of geodesics and the geometry of surfaces, with techniques applicable to higher dimensional manifolds. 1. Foundation for general relativity. Riemannian geometry enabled the formulation of Einstein's general theory of relativity. It provided the mathematical tools to describe the curvature of spacetime due to mass and energy. 1. Influence on other fields. The field has made a profound impact on group theory, representation theory, analysis, and spurred the development of algebraic and differential topology. 1. Riemann's legacy. Riemann's early education. Riemann's father, a Lutheran minister, initially taught him until he was 10 years old. Riemann showed a particular interest in mathematics and was allowed to study texts from the director of the gymnasium's library. 3. University studies. Riemann enrolled at the University of Göttingen in 1846, initially to study theology. However, he soon switched to mathematics, studying under great mathematicians like Gauss, Stern, and later Dirichlet in Berlin. 3. Recognition of genius. Although Gauss did not immediately recognize Riemann's genius, his other teachers, like Stern and Dirichlet, were aware of his exceptional talent. Dirichlet, in particular, had a significant influence on Riemann's mathematical development. 3. Bernhard Riemann's revolutionary ideas laid the groundwork for a new understanding of space and geometry. His work transcended the limitations of Euclidean geometry and opened up new possibilities for exploring the structure of the universe. Riemannian geometry continues to be a vibrant area of research, with applications ranging from theoretical physics to computer science. Parallel transport is a concept in Riemannian geometry that allows for the displacement of vectors along curves on a manifold while preserving their length and direction relative to the manifold's curvature. It's a way to compare vectors at different points on a curved space. Here's a detailed look at parallel transport. Definition: parallel transport. It involves moving a vector along a curve on a manifold such that the vector remains parallel to itself throughout the motion. Preservation of properties. The vector maintains its magnitude and the angle it makes with curves on the manifold, according to the manifold's geometry. Mathematical framework connection. A connection on a manifold defines how to differentiate vector fields along curves and provides the rules for parallel transport. Covariant derivative. The connection gives rise to the covariant derivative, which measures the rate of change of a vector field along a curve. Parallel vector field. A vector field, v(t) along a curve, \gamma t, is said to be parallel if its covariant derivative along the curve is 0, t, v(t) equals 0, where \nabla is the covariant derivative and \gamma t is the tangent vector to the curve. Geometric intuition. Example: on Earth. Imagine walking along a curved path on Earth's surface with a stick pointing in a certain direction. If you always keep the stick pointing the same way relative to the surface, you're parallel transporting it. Importance in Riemannian geometry. Geodesics. Parallel transport is closely related to geodesics, which are the straightest possible paths on a manifold. The tangent vector of a geodesic remains constant when parallel transported along the geodesic. Curvature. By examining how vectors rotate when parallel transported around closed loops, one can measure the curvature of the manifold. Applications. Parallel transport is crucial in physics, particularly in general relativity, where it describes how objects move in curved spacetime. In essence, parallel transport provides a way to navigate the curvature of a manifold, allowing for the coherent movement of vectors that respects the manifold's intrinsic geometry. Curvature in Riemannian geometry is a measure of how much a geometric space, known as a manifold, deviates from being flat. It's a central concept that captures the essence of the manifold's intrinsic geometry. Local and global curvature. Local curvature. At a small scale, curvature describes how space bends around a point on the manifold. It can be described by the Gaussian curvature in 2 dimensions, which is the product of the principal curvatures at a point. Global curvature. At a larger scale, curvature can give information about the overall shape and topology of the space. Mathematical description. Riemann curvature tensor. The most comprehensive measure of curvature is the Riemann curvature tensor, which is a mathematical object encapsulating all aspects of a manifold's curvature. It is defined as a commutator of covariant derivatives r x y z equals x y z y x z x y z, where x, y, and z are vector fields on the manifold, and \nabla is the Levi-Civita connection. 1. Sectional curvature. This measures curvature using 2-dimensional sections of the manifold. For any two linearly independent vectors, u and v, the sectional curvature is given by k u v equals u u v v u v2r u v u v, where \langle \rangle is the inner product defined by the Riemannian metric 2. Ricci curvature. This is the trace of the Riemann curvature tensor and provides a measure of how volume changes in the vicinity of a point. It's particularly important in Einstein's theory of general relativity. Geometric interpretation. Parallel transport. Curvature affects how vectors are parallel transported around loops on the manifold. If a vector returns to its starting point with a different orientation, this indicates that the space is curved. Geodesics. Curvature influences the behavior of geodesics, which are the shortest paths between points. In curved spaces, geodesics can converge or diverge. Applications. General relativity. In physics, the curvature of spacetime is related to the presence of mass and energy, as described by Einstein's field equations. Topology. Curvature is linked to topological properties of the manifold, such as the Euler characteristic, through the Gauss-Bonnet theorem. Curvature is a rich and complex property that has profound implications in both mathematics and physics, providing deep insights into the nature of space and time. Riemannian geometry, with its deep theoretical foundations, has a wide range of practical applications across various fields. Here are some notable examples. Machine learning. Riemannian geometry provides tools for understanding the structure of data spaces that are not Euclidean. For instance, it's used in algorithms for Monte Carlo sampling and Gaussian mixture model fitting 1. Computer vision. The field benefits from Riemannian geometry in tasks like 3D brain image analysis, image classification, action recognition, and motion tracking. It helps in dealing with data representations that involve shapes and curves. 1. Statistics. Riemannian geometry aids in the analysis of data lying on manifolds, which is common in high-dimensional statistics. It allows for more accurate models that capture the intrinsic structures of complex data. 1. Optimization. Many optimization problems involve spaces that have a natural geometric structure described by Riemannian geometry. This includes problems in signal processing and network analysis. 1. Physics. General relativity theory, formulated by Einstein, uses Riemannian geometry and its generalization, Finsler geometry, to describe the curvature of spacetime due to mass and energy. 2. Mathematics. Beyond its role in differential geometry, Riemannian geometry impacts areas like group theory, representation theory, algebraic and differential topology. 2. These applications showcase the versatility of Riemannian geometry as a foundational mathematical framework for solving complex problems in both theoretical and applied contexts. Riemannian geometry has found several innovative applications in the field of computer vision, leveraging its ability to handle data that lies on non-Euclidean manifolds. Here are some of the key applications. 1. Face recognition. By modeling face images as points on a manifold, Riemannian geometry helps in developing algorithms that are more robust to variations in lighting, expression, and pose. 3. 2. Activity recognition. The geometry is used to analyze patterns of motion, which can be represented as trajectories on a manifold, aiding in the recognition of different activities from video data. 3. Object detection and tracking. Riemannian geometry provides tools for better modeling of the shape and appearance of objects, which improves the accuracy of object detection and tracking in videos. 3. For texture modeling. The variability in textures can be captured more effectively by considering them as points on a manifold, leading to improved texture analysis and synthesis. 3. 5. Diffusion tensor imaging (DTI). In medical imaging, DTI data, which captures the diffusion of water molecules in the brain, is analyzed using Riemannian geometry to understand the brain's structure. 3. 6. Modeling shape variations. Shapes can be represented as points on a manifold, and Riemannian geometry helps in analyzing the variations and deformations of these shapes. 3. 7. 3D brain image analysis. Riemannian methods are applied to the analysis of 3D brain images, helping in the study of brain development and the diagnosis of neurological disorders. 2. 8. Image classification. The classification of images benefits from the geometric framework, as it allows for the incorporation of the intrinsic structure of the image data. 2. 9. Motion tracking. By representing motion as a path on a manifold, Riemannian geometry aids in creating more accurate motion tracking systems. 2. These applications demonstrate the versatility of Riemannian geometry in providing powerful and sophisticated tools for addressing complex problems in computer vision. In computer vision, Riemannian geometry handles shape variations by providing a mathematical framework to model and analyze shapes as points on a manifold. This approach allows for the consideration of the intrinsic geometry of the shape space, which is often non-Euclidean. Here's how it works. 1. Shape representation. Shapes are represented as points on a Riemannian manifold. This manifold encapsulates the essential features of the shapes while accounting for the variability inherent in real-world objects. 1. 2. Geodesic paths. The shortest path between two shapes on the manifold, known as a geodesic, represents the most efficient transformation from one shape to another. This is crucial for understanding shape variations. 1. 3. Precrusts analysis. Riemannian geometry is used in precrusts analysis, which aligns shapes by removing differences due to size, rotation, and translation. This helps in isolating the intrinsic shape differences. 1. For statistical analysis. The framework allows for statistical analysis on manifolds, such as computing the mean shape or the principal modes of variation within a set of shapes, which is important for shape classification and recognition. 1. 5. Invariances. Riemannian geometry helps in designing algorithms that are invariant to certain transformations, ensuring that the shape analysis is robust to changes in viewpoint, lighting, and other extrinsic factors. 1. 6. Computational tools. The field provides computational tools for optimization and inference on manifolds, which are used to develop algorithms for tasks like shape matching, segmentation, and tracking. 1. By leveraging the tools and concepts from Riemannian geometry, computer vision systems can more effectively handle the complex variations and deformations of shapes, leading to more accurate and robust applications. Dealing with non-Euclidean shape spaces presents several challenges, particularly in fields like computer vision and machine learning. Here are some of the key challenges. Complex geometry. Non-Euclidean spaces, such as hyperbolic or spherical geometries, have more complex structures than flat Euclidean spaces. This complexity can make it difficult to visualize and intuitively understand the data and operations within these spaces. 1. Generalizing algorithms. Many algorithms are designed with Euclidean geometry in mind. Adapting these algorithms to work in non-Euclidean spaces often requires significant modifications to account for the curvature and other geometric properties. 1. Data representation. Representing data in non-Euclidean spaces can be challenging because the usual vector space representations may not be applicable. New representation methods, such as embedding data into hyperbolic or spherical spaces, need to be developed. 1. Computational tools. The tools and operations used in Euclidean spaces, like matrix multiplication and vector addition, do not directly translate to non-Euclidean spaces. Alternative mathematical frameworks, such as gyrovector spaces, are needed to define these operations in a way that respects the underlying geometry. 1. Statistical analysis. Performing statistical analysis in non-Euclidean spaces is more complex due to the curvature and singularities. This affects how mean, variance, and other statistical measures are defined and computed. 2. Learning representations. Machine learning models that learn representations of data must be adapted to account for the nonlinear structure of non-Euclidean spaces. This includes redefining loss functions and optimization strategies. 1. Visualization. Visualizing non-Euclidean geometry can be particularly challenging due to its deviation from the intuitive flat spaces described by Euclidean geometry. This can make it harder to interpret and analyze the results of computations and algorithms. 3. These challenges require innovative approaches and a deep understanding of both the mathematical properties of non-Euclidean spaces and the practical aspects of computation and data analysis. That was all. Goodbye.